Welcome back. In statistics, finding the mean is guaranteed to show up on your exam, usually carrying a heavy 4 to 5 marks. Simply put, the mean is the mathematical average of a grouped dataset. We calculate it by taking the sum of all our frequencies and data points and dividing it by the total number of items. The most straightforward way to find this average is the direct method. Conceptually, it's very simple, but it introduces the first-place student stumble, calculating the class mark, which we represent as xi. Let's look at this table for the direct method. To find the class mark, we just look at our class interval. Take the first row, from 0 to 10. By adding the upper and lower limits together and dividing by 2, we get our first class mark, 5. From there, we multiply the student frequency by that class mark across every row. Add all those resulting numbers together, and you have your total sum. Plug that sum directly into the formula, divide by the total number of students, and we arrive at our mean, 23.80. The direct method works perfectly here. But when an exam question throws massive numbers at you, multiplying them manually becomes a liability. The larger the numbers, the higher the risk of simple arithmetic errors costing you full marks. To handle larger datasets safely, we use the assumed mean method. Looking at this second table, instead of multiplying large numbers immediately, we choose a number right in the middle of our class marks to act as a temporary anchor. We'll call this assumed mean A. Here, we've selected 21. Now we calculate our deviation, or DI, by subtracting our assumed mean from each class mark. Be careful here. Subtracting our anchor of 21 from a smaller starting number like 9 gives us a negative 12. Dropping the minus sign in these top rows is the most common mistake students make. Because we've shrunk the numbers, multiplying the frequency by this new deviation is much faster. We sum up that column, but to find the true average, we have to add our original assumed mean back into the final formula. But what happens if even those deviations are too unwieldy? We can shrink the data one more time using the step deviation method. As shown in this third table, we divide those deviations by the class size, which we represent as h. Since our classes step up by 2 each time, our h is 2. Now it's your turn. Grab your notebook, pause the video, and multiply the frequencies by these new u values. See if you can calculate the final sum on your own. Let's check your work. Looking at this completed step deviation table, we take that final sum, plug it into the expanded formula, and multiply it back by our class size. Just like before, we add our assumed mean at the end, bringing us exactly to our answer, 23.88. Notice that the final average remains the same regardless of the method. The assumed mean and step deviation methods don't change the math. They are tactical tools to compress large datasets. By working with single digits instead of triple digits, you completely bypass the risk of calculation errors when the exam clock is ticking. We've covered the 3 primary ways to find the mean. You'll see a fourth quadrant here labeled the combined method, but as you can see, it simply applies the exact same shrinkage principles we just learned, just organized into a different tabular layout. To master these calculations, map the formula directly to your table setup. The direct formula requires a column for fi, xi. The assumed method needs a column for di and fi di. Memorize which columns belong to which formula, and the table builds itself. Exam mastery requires strategy. Don't just start calculating immediately. Look at the dataset first. If the numbers are small, use the direct method. If they are massive, deploy step deviation. Choosing the right tool from the start guarantees maximum marks in minimum time. If this breakdown helped you simplify statistics, make sure to like, share, and subscribe. Keep practicing these tables, and we'll see you in the next lesson from Murkutes's Maths Academy.